Okay, so we're going to go back to doing classical mechanics. It's been a while since I did a video on this. What I've been doing is a lot of really long videos on special relativity and modern physics. And I'm going to keep doing those, but I'm going to probably shorten the lengths instead of doing, one 25-minute long video going through a classical or going through modern physics. I might break it up to doing a couple 10-minute videos on 3 different type branches of physics. And for this one, we're going to talk about classical mechanics. Particularly, I want to talk about time and reference frames in this video. So let me start off by talking about time, because that's something that needs to be discussed, especially if you're watching the series I'm doing on modern physics, where we're talking about special relativity. So according to, I'm going to say CM for classical mechanics because I'm lazy, and that's okay. According to CM, time is a single universal parameter that all observers agree on. Now we know that this is, well, if you've studied it or if you're watching along with the series now, this is not true. It is not true according to, I'm going to say SR, special relativity. So according to relativity, two observers in relative motion do not agree on all times. Do not agree on all times. And we actually just talked about this in the video. And just to show you, the Lorentz transformation, T prime, which is one observer, equals T minus U over C squared times X, all over the square root of 1 minus U squared over C squared. But notice, sorry about that, I'm trying a new system to upload and it's being a little weird. Anyways, so as I was saying here, or I was trying to get to say, what happens when this number is much bigger than this number? Or when this number is much bigger than this number? Well, what's going to end up happening is this is going to be essentially T prime equals, this is a really small number, close to 0. Oops. So this part essentially will get wiped off when you're dealing with really low speeds relative to the speed of light. And we're going to see something similar over here, because you're just going to have the speed of light and in the numerator some small number. So basically you'll get T prime equals T over the square root of 1, which is just T. So when you're dealing with really small velocities, speeds that aren't getting close to the speed of light, this is okay. This is fine to do. Now, in our series we're doing on special relativity, when you start going, 60% the speed of light, then it becomes noticeable. And we have to account for that. But for here, it's okay to say T prime equals T, and the big point here, that all observers agree on the time of all events. That's okay to do. Okay, so next up, let's talk about reference frames. Now, I put a picture of a reference frame up here. This is just a reference frame, and we can think of this as being a position vector R. All it is basically a choice in axes and origin. So what did we do? I'll use yellow. We chose our axes, in this case, Y to be up, X to be over here, Z to come out at you. And we chose our origin to be here. That's what the O here stands for. Now, we have to be wise about how we set up our origin, because, for example, if you have, let's say a block, if you have a block, if you have a block sliding down, sometimes it's helpful to think of one of your axes going along the direction of motion. In this case, one being perpendicular. It'll make it a lot easier because now you're just moving instead of moving in different X and Y components. You're moving in just one axis, in this case, the X. So hopefully that makes sense. Okay. The last thing I want to talk about for this is a special type of reference frame. So that was just above. So the special type that I'm going to talk about are called inertial frames. Inertial frames. And basically what that means is non-accelerating frames. Non-accelerating frames. So, I'll go ahead and mention, in these frames of reference, Newton's laws of motion, again, I'm really lazy, hold true. So an example might be, let's give the example. Let's say you're in a car. I'm going to draw this really ugly car. Okay? So we're in this car, and I'm a terrible drawer, but it's okay. Let's say here I am driving, and then you're riding next to me. You're over here. You're over here. If I'm going a cool, perfect, 60 miles per hour, you're not even going to really feel like you're moving. You're just kind of cruising along on the highway. Maybe you have it on cruise control. I know cruise control doesn't work perfectly, but, if it could, you wouldn't even notice that you're moving. You could juggle just fine. The Juggle Test is a funny one that people do. If you can juggle, okay, then you're in an inertial frame of reference. And basically what that's saying is, hey, if you were to juggle, the balls are going to go up and back down, just like if you're standing still. Now, let's say, this other car, sometime later, cuts me off. And I slam on the brakes. Well, if I'm slamming on the brakes, what's happening is, I'll use black. I'll have an acceleration vector pointing back. Let's see if I can draw that a little bit better. We're accelerating back when I slam on the brakes. Well, you're going to start going forward in the car, right? You're going to be like up here now. If you've ever slammed on the brakes, you're going to go forward. It's going to be really hard to juggle. That's because if you're accelerating, so accelerating frames, in this case when we slam on the brake, Newton's laws of motion don't apply. They don't hold. You couldn't juggle. If you tried juggling, you would go forward. It would be a mess. I can't even juggle when I'm standing still, let alone if someone slams on the brakes. And it goes the other way. Let's say I realize, oh no, I'm running late to work or whatever. So I'm going to go from 60 miles an hour to 70 miles per hour. Well, you're going to feel now, in this case, you would be accelerating this way, right? And what's going to happen? You're going to be pushed back in your seat. You know, if you've ever been on a plane, that's a perfect example. You're taking off and it speeds up really fast, and then you get pushed back in your seat. But then when you go in the air, you just kind of chill, and you could really probably juggle fine there. And then the other kind would be, so we talked about accelerating in that sense. What if we had merry-go-round? I can't draw it, but let's say you're moving around this circle. Okay? At constant velocity. Well, if you remember from our first physics course, you have centripetal acceleration. That's center-seeking. So there is acceleration. It's just centripetal acceleration. And if you try to juggle on a merry-go-round, you know, good luck, right? So those are non-inertial frames of references. Inertial frames of references are ones with no acceleration. So you're staying at the same velocity. Hopefully that makes sense, and I'll do more of these tomorrow.